this is a topic on conductors. Now the question is, what is a conductor? And what is the difference in the structure of the material that makes it a conductor or that makes it a non-conductor? A conductor is something that has got free electrons. Now again, what are free electrons? Free electrons are the type of electrons which are not attached to a particular atom or a nucleus. So let's say this is one nucleus, positive charge of course, and there are a lot of electrons around it. And in the same matter, in the same material, there is another nucleus and there are also electrons around it. You might see that there is an energy level here at this point. We can mark it. There is an energy level here. If this particular electron here, let me show it in different color. If this particular electron here, there is an electron here, it will experience equal forces from the respective nuclei, and it will be confused whether it belongs to the nucleus here or it belongs to the nucleus here. So such an electron which is not a part of, let me put it this way, not a part of a specific atom, or in other words, which experiences similar forces from neighboring atoms, is a free electron. So this is a free electron, this is a free electron here. Now if we take another electron, let me take it a different color, let's say an electron here, this electron will know, the red electron, that electron will know that it is experiencing more force from the nucleus to the left and less force from the nucleus to the right. So this particular electron, the red electron, belongs to the left nucleus, or should I say nucleus A and nucleus B. So the red electron belongs to nucleus A, and if we take another electron, let's say here, the green electron belongs to nucleus B. But if we have a look at the blue electron here, we can say that it effectively does not belong to any nucleus, as it might experience equivalent forces, almost similar forces from all nucleuses that are nearby. So such type of electrons are called as free electrons. Now what are the properties of free electrons? I think there is only one property that is very important right now to understand, is that since a free electron experiences equal forces, we can say more or less equal forces, but chalo, equal forces from all neighboring nuclei, it is free to roam about, it is free to move in the conducting material. It can easily move about in the conducting material, and that's the most important property of a free electron that I can tell you. And how this property is going to help us to understand how conductors behave if you do understand this property and just this property, you will eventually know how conductors behave. So now we are coming to the behavior of the conductors. So let's say that we have a conductor here. And since it is a conductor, it has got a lot of free electrons in there. Okay, so this is our conductor here. Now, there are electric fields here that are passing through the conductor, also passing through the nearby space. This is an electric field here. Now what happens if you apply an electric field in a material that has a lot of free electrons? The material has a lot of free electrons. Basically every atom releases one free electron, so you can have a lot of free electrons. And what will happen then? So the electrons will experience force. That will be simple, E into E. And you must know that since electronic charge is negative, so force and field will be opposite in direction. So the electrons will experience force in what direction? The electrons will experience force in the reverse direction, in the backward direction, like this. So what is going to happen is this. All the electrons will start to assemble at this point. All the electrons will start to assemble at this point due to the force. And when the electrons start to assemble at this point, and the conductor was initially neutral, you must remember that the conductor was initially neutral. So if the conductor was initially neutral, you will have a residual positive charge here. So negative charge here and positive charge here. The thing that is going to happen is this. There will be a reverse field, and this reverse field will be called as the induced field. So there is an original field that you see blue in color, and there is an induced field that you see black in color. And what happens in a conductor is simply this. Since there is no scarcity of electrons, somewhere I have to write it. Okay, so I'll write it here. Since there is no scarcity of electrons, the field is produced such that the induced field plus the original field become equals to 0. Or we can say that the net field becomes 0. And that is the most important property of a conductor, and that we can say it is the property number 1. That is the first property. Okay. Or the most important property in a conductor is that the net field inside the conductor will be equals to 0. And we must remember that we are not talking about the original field or the induced field. Let me draw it again for you. This is the original field, and this is the induced field, and only inside the conductor, just inside the conductor, E induced plus E original equals to 0, and the net field becomes equals to 0. The net field in a conducting material is always 0. You can write this if you want. Now, coming back to the conductor, if the net field here is 0, there is no field at all, we can say very simply the following. Let's say there is a point A here, there's a point B here, there's a point C here, there's a point D here, there's a point E here, there's a point F here. And if the field inside is 0, we can always say that VA equals to VB equals to VC equals to VD equals to VE equals to VF. That means all points inside the conducting material, I'm repeating it again, all points inside the conducting material are at the same potential. To the conductor, okay, so we'll draw the conductor again. This was your conductor, and there was an original field. If I remember, it was in blue. This was your original field, and then there was an induced field that we had drawn in red, and the net field inside the conductor, became equals to 0. Now, how will the overall field look like? Now we know that all points inside the conductor, not just on the surface, any point inside the conductor are at the same potential. Now if all points are at the same potential, that means they form an equipotential surface. If they form an equipotential surface, we know that field lines are always perpendicular to equipotential, and let me write it in short form, surfaces. Field lines are always perpendicular to the equipotential surfaces. So if you have field, like this, and then there was an induced field, but what happens after everything is sorted out, after everything is clear and done? So we have fields like this that fall on the surface of the conductor exactly at angles of 90 degrees. You must see all angles are 90 degrees, even these angles are 90 degrees, and they come out of the surface of the conductor also at 90 degrees, and there were some field lines that weren't passing the surface of the conductor. They still aren't passing the surface of the conductor, but the ones that are passing the conductor will terminate at 90 degrees, and then from the other side will emit at 90 degrees. This is very important for you to understand. All the field lines that cross the conductor will terminate the surface of the conductor at 90 degrees and will originate the surface of the conductor at 90 degrees. Now we have to write down the two rules that we have studied right now. So the second rule was all points on the conductor are at same potential. So the entire conductor becomes an equipotential surface. And the third rule was field lines terminate or originate from the surface of the conductor at 90 degrees. So we have three laws. All points inside the conductor, at all points inside the conductor, the field will be equals to 0. First law. Second law, at all points inside the conductor, the potential will be same. That automatically comes from the fact that the field is 0, so the potential, there must be no potential difference. We all know that field is equals to minus dV by dr. So if field is 0, obviously then the change in potential or the potential difference will also be equals to 0. Now the third law comes from the fact that if we have an equipotential surface, let's say this is an equipotential surface, the field lines will always come out or terminate at 90 degrees. Or if we have this kind of an equipotential surface, again the field lines will come out and terminate at 90 degrees. So these are the three laws that basically form the fundamental concepts behind the understanding of a conductor. And there are more laws, we are not getting into those laws right now, and we'll get into them step by step as we start to understand how conductor works. Let's consider a spherical conductor, and let me draw it. This is a spherical conductor, and there's a charge Q that is outside the conductor, and due to this charge Q there will be field lines both inside the conductor as well as out. There is no denying that. But what will happen to the electrons due to these field lines? So as we told you, the electrons will experience an opposite force. In what direction? Towards right, obviously. So what we'll see here is basically an assembly of electrons, a high density assembly of electrons at this point, which will slowly decrease on, and then since the conductor was neutral at the first place, we will see an assembly of positive charge on the other side. And due to these charges, there will be an induced field. And this induced field will cancel out the original field. How is this conductor going to behave? So we have a charge outside. We have a charge outside, and that outside charge is spreading out fields in all directions. And when I say all directions, I really mean all directions. I haven't drawn them, but you can assume the charge is emitting field in all directions. But we are interested in the field lines that pass from the conductor. Due to these field lines, the electrons will experience force towards right, and there will be a residual positive charge on the left side. So there will be an induced field, that's what we call it, an induced field, E induced, that will cancel out the original field E inside the conductor. So how is the behavior going to be? So if this is your charge, the field will fall at 90 degrees, not very good drawing, but you'll have to assume field lines will fall at 90 degrees to the conductor. Again, not very good drawing, but you'll have to assume the field will fall at 90 degrees to the conductor. All field lines will fall at 90 degrees to the conductor, and from the other side they will be again emitted at what angles? Again 90 degrees. Again they will be emitted at 90 degrees to the conductor. So all these angles that you see are at 90 degrees, and the field inside, the net field inside, will be equals to 0, and the potential of all the points that are inside will be same. The potentials at all points will be same. Okay, so this is our conductor again, and as I had told you, the charge is outside Q. And now let me assume some specifics of the conductor. So we have a center of the sphere, that is C, and we have a general point, let's say this point as P, and we are going to discuss everything that we can about these 2 points. So first of all, let's come back to the basics again. I told you there were field lines due to this charge Q that were passing through the conductor. Due to the field lines, there was an induced charge, and the induced charge was equal and opposite. So if we have a negative charge here, we will have equal amounts of positive charge on this side, simply because the conductor was initially neutral. So negative and positive charges will be equal. And now we are going to discuss a lot of things. We are going to discuss what is the field at C due to Q. Only due to Q. We are not talking about the induced field or any other field. We are simply talking about field at C only due to Q. So the field at C only due to Q is going to be something like this. For example, if you assume the distance between C and Q to be R, so the field will be something like this. So the field at C due to Q is going to be KQ upon R squared, and in the direction of the green arrow that I have shown. And the next question is obviously, what will be the field due to induced charge at C? Now we know that induced charge is quite complex. There is some positives, there are some negatives, so it becomes really difficult to calculate. But if we know one thing, and what is that thing? We know that the net field is 0. Net field is 0. And what is net field? The net field is basically the original field plus the induced field. So we can get the induced field as negative of original field. Negative of original field, that I'll draw in the diagram. Negative of original field means in the opposite direction. This will be your induced field, and this was your original field. And it is such that both fields cancel out each other. So the induced field, the value of induced field, not discussing the directions, the value of induced fields will also be equals to KQ upon R squared opposite to that of the original field E. Now it comes to other points. Let's say a general point P, as I have shown in the diagram. So this is our general point P, and I'll have to move this out of the scene. Let's consider that again. This was our conductor, and again there was a charge Q. This was C, obviously, this was P, and let's assume some distance here. Let's say the distance between this is R dash. So again, the next question, the third question, is going to be field due to Q at point P. And it is very simple. It is going to be KQ upon R dash squared, and the direction of the field is going to be obviously in this direction, because we are assuming the charge Q to be positive. And then comes the next question. Induced field due to the conductor at P. So again we will apply the same concept. We know that E plus E induced is equals to 0 at all points inside the conductor. So if the field E induced and the net field is 0 at all points inside the conductor, we will simply get E induced as negative of E, and negative of E would simply mean that the induced field is in the opposite direction. And magnitude wise it is going to be same, so the induced field can be written as KQ upon R dash squared. KQ upon R dash squared. Again it's the same conductor, so charge outside obviously, and this is C and this is P obviously. So now we are going to discuss some other things, like the fifth question. Let's say the fifth question asks, what is the potential at C due to Q, small q? Now you know that we have already discussed the distance, and the distance was something R. So the potential, the formula of potential due to a point charge is very simple. The potential is coming out to be KQ upon R. Now I want you to focus at the sixth question. This one is important here. What is the potential due to induced charge at C? Now we all know what induced charge is. There was accumulated positive charge here and there was an equal amount of negative charge here. So that was your induced charge. So we want to know what is the potential at C due to induced charges. For this we'll have to assume the radius of the sphere. So let's say the radius of the sphere is capital R. Now you all know that whatever charge has accumulated, all the charge has accumulated on the surface. Why on the surface? That's an important question. Simply because the charges cannot go beyond the surface, they cannot fly into the air. So that is the farthest point the field can push the charges, or the farthest point the field can push the charges here. So they will take the farthest points that they can be pushed, and so we can easily say that all the charges accumulated on the surface. Now there are more reasons and more logic to it, but we are not going into that right now. For the face value basis, the charge has accumulated on the surface. Now what is the potential going to be? Now we all know that there is some positive charge, let's say plus q, and there is some negative charge, that is minus q. And since all of them are on the surface, it's very important to know all of them are on the surface, then all of them have equal distances from point C. And what is that equal distance? Obviously the radius of the sphere. So the potential due to induced charges will be written as kq upon r minus kq upon r. The first one due to the positive charges obviously, and the second one due to the negative charges obviously, and all charges are at same distance, that is r. So the net potential becomes equals to 0. So induced potential becomes equals to 0. So what is the total potential? V total will be V due to Q plus V induced. Now you know that V induced is 0, so it only becomes V due to Q, and that is equals to KQ upon R. Now we move on to more questions, and for that I have to shift the page for you. So let's look at it again. Again, the charge Q, this was C, the radius of R, the radius was R if you remember, and now we are discussing about a certain point P. So my next question obviously is, what is the potential due to Q at P? And we all know that, what do we know? We all know that the distance was R dash. So the potential becomes very easy to find, V equals to KQ upon R dash. Now we come to the last and the most important question in this explanation, and that is, what is the potential at P due to induced charges? So again, I told you, the induced charges are the charges that are formed on the surface, equal positive, equal negative. But now here is the problem, there is no symmetry. The point P is here, the point P is here, and it is closer to some charges, farther away from some charges, and more farther off from the negative charges obviously. So it will become very difficult to find out P if we want to find out potential at P directly. So we are not applying a direct method, we are applying the indirect method. And what is the indirect method? We know if E equals to 0, then dV equals to 0, there is no change in potential, and if dV equals to 0, then it becomes obvious, isn't it? Vc becomes equals to Vp. The potential at C becomes equals to potential at P. Now let me remind you what was potential at C. The potential at C was potential due to Q plus potential due to induced charges, and the potential due to induced charges was 0, so the potential at Q was simply equals to KQ by R. And if you might remember, what was R? R was the distance between C and Q, right? So the potential at C is basically equals to KQ by R. And then if we know the potential at C, and we know that there is no change in potential because the field inside the entire conducting surface is 0, then we know that potential at P is equals to potential at C, and we can simply say that potential at P equals to KQ by R. Now you must understand here that potential at P will be formed due to two reasons. The first reason is obviously potential due to charge Q, and the second reason will obviously be potential due to induced charge. Now we don't know what potential due to induced charge is because the arrangement of induced charges is very complex, and in order to find the individual distances and then integrate them becomes hell of a job. We are not doing that. But we know something else. What do we know? We know that the potential due to charge Q at point P obviously is this. What is this? KQ by R dash. What was R dash? R dash is this distance. So the potential due to induced charges can be written as Vp minus V due to Q, that is equals to KQ by R minus KQ upon R dash, and that is the potential due to induced charges at point P. Let me write this, at point P. Now we are going to discuss conductors that have some kind of cavity. So let's say this is a conductor and there is a cavity inside the conductor. Let me fill the gap in between. Okay, so this is what we have. We have a conductor, and then inside the conductor there is a cavity. Now let's say there is a charge outside, and let's say here there is a charge outside. Now again this charge will emit fields that will pass through the conductor. Some fields will not pass through the conductor obviously, and then what's going to happen? The negative charge on the conductor will assemble on the left side, on the right side, and the positive charge, equal positive charge on the conductor will assemble on the left side, and there will be a field, that will make the entire field inside the conductor equals to 0. So the net field, the red one is, as you can see, is the induced field obviously, the green one is the original field, and the net field inside the conductor will become equals to 0. So if we have a conductor like this, drawing it again, and if there is a cavity inside and I want to fill up the space to make it clear. Alright, so this was the charge. So the field lines will fall perpendicularly, as we discussed. The field lines will fall perpendicular to the surface, all at 90 degrees. Not the ones that are not passing through the conductor, they will pass their own way, no one is disturbing them. And on the second side, the field lines will be emitted again at what angles? They will be emitted at 90 degrees to the surface of the conductor. And the field inside will be equals to 0. And nothing special happens if the conductor has a cavity. It behaves almost as if a conductor that was with no cavity. But a lot of things change when the cavity itself has a charge. So let's see what we're discussing about here. So we have our conductor again, and we have a cavity here, and again fill it up with some color, you see. Now this cavity has, how do I put it? It has a charge. It has a charge Q. It has a charge Q. And there is a charge outside, that is capital Q. But right now we are not discussing what is happening on the outer charge. We have discussed that at length. We are right now interested what is happening due to the blue charge that is inside the conductor. Now, the idea was that the blue charge would emit fields in all directions as usual. And since the yellow region is a conductor, obviously there will be some induced charges, negatives, as you can see here on the surface, and there will be positives on the other opposite surface. As you can see, the same thing happens, and there will be an induced field in the opposite direction, and that induced field is going to cancel out. This is your induced field, obviously, and this is your original field, and that induced field is going to cancel out the original field in the surface of the conductor. So how do we deal with this situation, and what finally appears after we have done everything and after we have taken track of everything? So this was our conductor. Again, let me fill it with color, and there was a charge inside. And what was going to happen after everything has been done and considered with? The charge will emit fields that will fall at 90 degrees. It may not appear in the diagram or you might get confused, so I am drawing the angles. The fields will fall at 90 degrees, but there is no field in this region. The net field is obviously equals to 0. There is also a negative charge here, and then there is also positive charge, equal positive charge here. And due to this positive charge, the field lines will be emitted from the surface of conductor, again all at what angles? 90 degrees. So we have a discontinuous system here where there is a field inside the cavity due to the charge. Obviously you can see there is a charge inside the cavity, so there must be a field. This region is not conducting, and as we had discussed, if a region is not conducting, it is not necessary to have zero field there. Zero field exists only in the conducting region, that is the yellow region that you are seeing here. So there is a discontinuity of fields. The fields are emitted from the positive Q charge, terminate at the inner surface of the cavity at 90 degrees. There is no denying that, at 90 degrees. And then there is a discontinuity here, and from the positive charge the field lines are being emitted again at 90 degrees from the surface of the conductor, and those field lines will terminate at infinity. For more questions and further discussion, you'll have to wait for my second video on conductors part 2.